It's my pleasure today to introduce Pablo Rodriguez-Fernandez, who's going to give today's IAP talk. He came to MIT from Madrid, Spain in the fall of 2015 for the PhD program in plasma physics. He worked out of Ann White's group on transport modeling for plasmas in Alcator CMOD, Aztecs Upgrade, and JET. Graduated in 2019 and won a departmental thesis prize. And this was for work on uncovering the mechanism of the so-called cold pulse, which is a phenomenon that had puzzled people actually for a number of decades. So that was quite an accomplishment. After graduation, we convinced Pablo to stay on and continue as a postdoc here at MIT. And he's dividing his time between research on JET and Aztecs Upgrade as a collaborator and also on SPARC, where he's part of the physics team. Probably also worth noting, he was recently named by Forbes magazine as one of 30 under 30 in science. So he's something of a celebrity in the popular press as well. So whenever you're ready, Pablo.
All right. Thank you very much, Martin, for the introduction. And hello, everyone. It's really a pleasure for me to be here today with you virtually to talk about fusion energy and how we see fusion energy happening here at MIT and about the SPARC tokamak. I would like to start by thanking a number of people that have contributed directly with feedback and input to this talk: Nathan Howard, Ryan Sweeney, Martin Greenwald, Alex Greeley, Bob Mamger, and Brander Sorbonne. So thank you very much for your input. So as every fusion talk or energy talk, we need to start by talking a little bit about the climate. There aren't enough words to emphasize that we need a new energy source and we need it soon. Most energy generated worldwide still comes from burning fossil fuels. Here on the right, you can see a graph of the world energy consumption by source since the 60s up to basically today. And more than 80% of our energy comes from burning fossil fuels, basically from dumping CO2 and other harmful gases to the atmosphere. And this doesn't come without a consequence, of course. Climate scientists have told us for a long time now that climate change is going to be the next big challenge that humanity will have to face. And by now, we all know what are the consequences of a world crisis, how that affects every aspect of our lives. So we really need to listen and act soon. It is true that we are late to many aspects of this. I don't want to be overly pessimistic, but that's true. We're going to have to face challenges, but we still have time to make a difference and at least not making it worse. We know the consequence of climate change. About 40% of world population lives around coasts, which means that the rise of the sea level is going to be a big problem. Extreme weather events, temperature anomalies, all these things are things that are happening now, and they will get worse and worse if we don't do anything about it. Not only we need to reduce CO2 emissions at current power generation levels, but also demand is growing. A fact is that industrialization of societies comes with an energy cost. And as the world develops further, we're going to need more and more energy. Here, I'm plotting the US electricity generation. So only electricity generation, which is already a small part of the entire energy consumption. We have data from 2010 to 2020 and their projections up to 2050 by the Energy Information Administration. Even assuming a steady growth of our renewables, wind, solar, and others, and assuming a constant capacity of our fission power plants, by 2050, we're going to still be generating our energy, 50% of our energy from burning fossil fuels. So we need to do something about it. We need to substitute that baseload power that fossil fuels provide. We need a new energy, a new technology. And that new energy, whatever it is, it has to have the following, it has to meet the following requirements. It cannot emit greenhouse gases. We don't want to make the problem worse. It has to have abundant fuel supply because we don't want to worry about this problem from some decades from now or even a century from now. We need something that is safe for humans, safe for our environment, that can be available for baseload power generation, and that is scalable, that is dispatchable, that fits into modern grids. We don't want to change the entire energy infrastructure in the next few years. And at the MIT Plasma Science and Fusion Center, we believe that fusion energy, can have a role in solving this problem. And today's talk is going to be about fusion in general, and we're going to end up with how we see fusion here at MIT. So what is fusion? Fusion energy is a basic physical process that releases large amounts of energy. It involves light nuclei and is the energy source of stars. Actually, in reality, most forms of energy that we use here on Earth originally come somehow from the fusion reactions in our sun. So basically what we want to do is to get rid of all those middle parts and exploit directly here on Earth fusion energy. And fusion sometimes, well, most of the time, comes with the name of nuclear fusion, and it's important not to confuse it with fission. So it has the name nuclear because it involves the nucleus of atoms. And here on this is a very typical graph of that is used in the nuclear physics community. It is the average binding energy per nucleon as a function of mass number. So we have here all elements in our periodic table organized. And you don't need to know the details about what this binding energy really means, but you just need to know that the higher in this curve, the more stable the nucleus is. Basically, the happier the protons and neutrons in the nucleus are. And it turns out that moving upwards in that curve towards stability releases energy. And that is what our colleagues in fission do. They take a big element of large mass, like uranium or maybe plutonium. They split it up in two parts, and that moves the system towards higher stability. And that releases a lot of energy. What we want to do instead in fusion is to do the opposite process. We want to take light elements, hydrogen-like elements. We want to combine them together. And because you moved upwards in this stability curve, you also release energy. However, the nucleus of atoms are particles that are positively charged and therefore repel each other. There's this Coulomb electric force that makes them repel each other. So one question that one may ask here is like, okay, so how do we make them fuse? How do we combine them if they repel each other? So one solution to that is to say, okay, there is this Coulomb force that prevents them from getting close to each other. But what about if we have them have high speed and we make them collide? Then they may fuse. That's actually, if we look into this in more quantitative or like more physics terms, what that means is that we need to give enough kinetic energy to the particles to actually overcome this Coulomb electric repulsion and get them close enough together so that a different force in nature, the strong nuclear force, which is attractive, wins, and we get them combined and we fuse them and we release a lot of energy. However, if you take pen and paper and you calculate what's the kinetic energy that you need to give a particle to overcome that Coulomb barrier, and actually you do that with a lot of particles in a system, so you have a thermalized system, and in a system like this, temperature is just a metric of the average kinetic energy. So you calculate what the temperature of the system needs to be to overcome that Coulomb barrier, and you end up with a very, very big number. You end up with 3 billion degrees. That's very, very high. If you do a more detailed analysis, you realize that there is something that helps you, which is quantum physics. There's an effect called quantum tunneling. So you don't need to give kinetic energy to the particles to go above this hill. There is a tunneling effect that happens with some probability that helps you in this process. So the temperature, instead of being 3 billion degrees, you're talking about 100 or 150 million degrees. However, even if that has helped, this is still very, very hot. So one question that one may have is this a showstopper to fusion? Because if we need to have the system at 100 million degrees, how can we contain it here on Earth? What kind of materials we use to contain it in the lab, basically in a reactor? So what we do, and in magnetic fusion, what we do is to take advantage of one property of these systems. So the elements at fusion temperatures, this hydrogen at fusion temperatures at 100 million degrees, is not a hydrogen gas anymore. Instead, is in the form of a plasma, what sometimes is called a soup of charged particles. Plasma is considered the fourth state of matter. We have solid, we add heat to a solid like ice, we melt it, we have a liquid. We add more heat and we get a gas. And if we keep adding energy, we eventually get a plasma. A plasma is basically, in broad terms, it's a gas where we don't have atoms anymore as entities of the system. We have charged particles, electrons and ions, nucleus going around, interacting with each other, but not in the form of atoms. And it turns out that the motion of charged particles is affected by electromagnetic fields, by electric and magnetic fields. And that is great, because if you're able to create a magnetic field, you have your very energetic particles gyrating around that magnetic field, so you can control where they are. And if you do this carefully, you can keep this very energetic system away from the walls of physical materials of your reactor. And if you take that magnetic field, you make it in a loop, you close, basically you get rid of the ends, that leads to a plasma confined in a toroidal or donut-shaped chamber, and you have your particles gyrating around this closed system. And that's it. You then build a machine around this. You have some big coils that generate that magnetic field. You put some heating systems around it, and then you get your plasma. And simple enough, that's what the tokamak device does. Tokamaks is a type of machine that we use in fusion, and it has two key features. One is that it has a toroidal field coil, which are these big guys here. We have about from 16 to 18 of them typically around the machine. And these coils, these electromagnets, generate a toroidal magnetic field in this direction. So you see here in blue, the toroidal direction. However, it turns out that a purely toroidal field cannot confine the particles. You don't need to know details about this, but just to know that if you have this curved toroidal magnetic field, the particles will eventually leave the system and hit the walls of your machine. So you need another component of the magnetic field that we call the poloidal, which goes in this direction. And in tokamaks, we generate that poloidal magnetic field using a solenoid, central solenoid that we put in the center of the machine that acts as a transformer circuit and induces an electrical current in the plasma in the toroidal direction. And that electrical current comes with an associated magnetic field. Basically, we have self-consistent generation of the poloidal component of this magnetic field. So you end up with a helical structure of your magnetic fields in the plasma, and that confines the particles to be in the center. Good. And we have a lot of experience with these machines. This is the Fusion Device Information System. It's a database of machines around the world by the IAEA, International Organization. And we have about 55 of them operating in the world right now. We have built about 170 of them, all these tokamaks. So we have become really good at building, operating tokamaks, working with them, optimizing them, build these machines for many, many years now. So one question that you may have, of course, is that, okay, if it's that simple, if we have built these machines before, have we achieved fusion? And the answer to that is yes. In all those devices, we have fusion reactions. We measure the products of those reactions every day around the world. We measure those neutrons that comes from the reaction. However, and here's the catch, the energy that is required to have those reactions happening in degrees, you require more energy than you eventually produce with fusion. There is a metric that we use in our community called fusion gain, or Q plasma is called sometimes, which is the ratio of the power produced by fusion divided by the power that is required to maintain the reaction going, that goes into the plasma. And the record of that number has been 0.6. It was by the JET tokamak in the UK. It's a European project in the 90s. And we have never reached what is called break-even, which means this guy equal to 1 or greater than 1 in a situation in which we generate more energy than we actually consume. This plot is a little bit outdated, and you really don't need to know what these two things mean. I just want to show you that we have built and operated a lot of machines over the years, and we have gotten closer to this break-even point in which we produce as much energy, at least, as we need to keep the reaction going. But we have never crossed that line. And of course, if we want for fission to make sense as an energy source, we need that ratio to be above 1, and hopefully much greater than 1, because you want to account for inefficiencies in your system, and you want to produce a lot of energy. So there are generally 2 ways to make that happen, 2 ways that we are pursuing around the world to make that happen. One is to have bigger machines, that means bigger radius of the torus of this tokamak, or to have higher magnetic fields. And for the next about 5 minutes of this talk, we're going to dive into the physics, a little bit into plasma physics, to understand why those trends are true, why size and magnetic field are 2 very important parameters in tokamaks. And to do that, we're going to start with nuclear physics. We're going to move a little bit to plasma physics, and then we're going to talk about tokamak parameters. So nuclear physics gives us a very nice expression for how much power you generate with fusion. The total power in watts is equal to the product of the density of your fuel, in this case is deuterium and tritium, 2 isotopes of hydrogen, times the reaction rate coefficient, so how often those 2 particles collide, the energy that you produce per reaction, and the volume of the plasma where those reactions are happening. And to continue this derivation, we want to get rid of this guy here, the reaction rate. So we look at data of what is the reaction rate of different reactions. So what I'm plotting here is the reaction rate coefficient as a function of temperature. In plasma physics, we use a unit called kV, kilo electron volt, and 1 kilo electron volt corresponds to 11 million degrees. So we needed a smaller unit. There are 4 reactions here between 4 different isotopes, 4 different nuclei. The reaction that is more frequent is the DT reaction, a reaction between 2 isotopes of hydrogen, deuterium and tritium. And that reaction is orders of magnitude more frequent than any other and more energetic. So that's the one that we're going to be using in tokamak fusion. In the region of interest, which is going to be around this part here, about between 100 and 200 million degrees, the reaction rate coefficient actually behaves as the square of the temperature. It's a log-log plot, so it's basically linear in this part. So we're going to make that simplification, and we're going to get rid of all proportionality factors here. We're just going to carry orders of like how the parameters behave. And we're going to also assume 50-50 mixture of your 2 isotopes, 2 particles, deuterium and tritium. Then that expression becomes something very, very simple. The fusion power per unit volume becomes proportional to the square of the pressure. Here we are just pressure N times T. We forget about the Boltzmann factors here. We're just looking at parameters. And that's very nice because plasma pressure appears as a direct measure of fusion performance. That's a very nice, simple formula, conceptual formula. And we're going to keep it there to remember. So, okay, so if you want to produce a lot of fusion per unit volume, you need very high pressure. So can we actually just increase the pressure of the plasma arbitrarily high? And the answer is no. And we have learned that kind of the hard part, like a long time ago. There is a limit on how much. There's a limit on how much pressure you can actually contain in your tokamak, in your magnetic field. What I'm plotting here is the normalized pressure, so the thermal pressure over the magnetic pressure, as a function of a tokamak parameter, which is electric current over the minor radius of the torus times the magnetic field. And it turns out that the maximum pressure that is achieved in a number of devices is linear with that parameter. Above that pressure, the plasma becomes unstable and you cannot operate. So it makes sense to rewrite our formula of the square of the pressure with a factor that we call the normalized beta. This normalized beta has to be below some given value. So, okay, we have that limit. So if you want to have high pressure, you may want to have high electric current. Well, there's also a limit on how much current you can have in your device. And that's given by something we call the rotational transform, or the inverse of the safety factor. So as I said before, in tokamaks, we have a helical magnetic field. And that metric is related to how the magnetic field is bent. how many poloidal transits, so how many things you do like this, per toroidal turn, per toroidal transit. So there is a limit on how high that value can be. So there is also a limit on the plasma current. And we have learned that for many years. This is kind of a confusing plot, but just to know that since the 80s, we already know that these limits exist and we cannot go over them. So, okay, so we have those two things. So it makes sense to rewrite our expression as a function of those two parameters. So we end up having a stability parameter, we have a geometric parameter, and then we have a magnetic field. Here we have used the aspect ratio of our torus, minor radius over major radius. And this is the elongation, how stretched the plasma is. So to avoid those regimes that I was telling you before of an instability and avoid that the plasma disrupts and you lose confinement and you lose fusion power, we're going to choose that stability factor to be below some certain threshold. So basically, there is a maximum value of that factor that you can use. Also, it turns out that the this geometric factor with the aspect ratio and elongation, it's only geometric, and for standard tokamaks, it does not vary significantly. You can see here in this plot a bunch of experiments, different machines, how elongation in the y-axis and aspect ratio in the x-axis varies. It's basically within a very narrow range, and we don't want to operate in uncharted regimes, so it makes sense to choose that value within what we believe we understand, because we don't want to have instabilities in the plasma that we have studied and modeled for many years. This is, for example, in 1950s, a column of plasma, nice plasma here.
Excellent speaker.
Sorry? Somebody is unmuted? Anyway, so I was saying that the plasmas can suffer from instabilities. Very nice, you can see it here. And this is something that you want to avoid in tokamaks, in future devices too. So if there is a maximum value for those parameters, then your fusion power per unit volume becomes just proportional to the fourth power of the magnetic field. And if you convert that volume into an R cube, having an R cube dependence of your plasma, then you end up with a total fusion power having this form, this expression. And similar trends can be derived for the fusion gain. I'm not going to go into this, but you just take the same kind of rules and you apply them to that metric, and you end up with an expression that is very similar. So with these very simple rules, we already see that the magnetic field has a very, very strong effect on performance, on fusion power. The magnetic field appears with a fourth power in terms of fusion power density. So this is a very, very strong dependency. So high magnetic fields lead to higher plasma performance. We have seen that. And MIT has been the leader of the world's high field fusion approach for many years with a series of experiments called Alcator experiments. The last one was Alcator CMOD. It operated for over 20 years on MIT campus. And the last day of operation in 2016, with Alcator CMOD, we broke the world record of plasma pressure ever achieved in tokamaks. We did that in the last day of operation. It appeared in the news. It was a huge thing. Here I'm plotting the raw data of that plasma discharge, of the record plasma discharge. We reached about 2 atmospheres of pressure, 30 million degrees, and a lot of fusion reactions per second. So this was really, really exciting. So, okay, so plasma physics, we see that plasma physics likes magnetic field, high magnetic fields. So the question is, can we then build machines that produce arbitrarily high magnetic fields? We can construct contour plots like this one with the fusion gain, fusion performance as a function of size, this linear size, the major radius of the tokamak, and the magnetic field. And both size and magnetic field helps with fusion gain. The problem is that for many years, there has been a limit on how high you can have your magnetic fields, and that's an engineering limit, a materials limit, or how high the magnetic fields can be generated with standard superconducting technology, what they are called the low temperature superconductors. And actually, ITER has long been the leading fusion project. It has aimed at reaching the net energy break-even fusion milestone. And when it was designed with the highest magnetic field that it was achievable with the standard magnet technology by the time. And if you have that limit on the magnetic field, if you want to produce a lot of fusion and having a lot of fusion performance, you need to build it very, very big. And the major radius of ITER is above 6 meters. And that has a consequence because that makes the project very expensive, very complex, very slow, requiring the collaboration of several nations. And the goal of ITER is to reach that break-even milestone, the Q greater than 1 with DT fusion in 2035. So let's look at the roadmap of how fusion, what fusion looks like following these trends here. So right now we have a lot of devices around the world. You saw that we have over 50 tokamaks operating. The largest tokamak we have is JET in Europe, in the UK actually. And we use these devices to study plasma physics and the safe operation of tokamaks. The next step is going to be ITER. ITER will demonstrate net energy. It's now midway construction, and we will have first plasma in 2025. And the Q greater than 1 and the goals of performance by 2035. It's going to cost more than $25 billion, and it will not generate electricity. It's going to be just to study those net energy burning plasmas and demonstrate that fusion is feasible. The next step is something that sometimes we call demo, the demonstration of energy, electricity generation. There are several designs under consideration by different countries, and it's likely going to be larger, more expensive than ITER. Here's everything, I put everything to a scale. So something that we have to ask ourselves, some kind of self-critique to the fusion community is, if fusion reactors need to be this big, are we ever going to be economically competitive? And let's come back to the plot that I showed in my first slides. I showed you the projections for the US electricity generation, and I told you that we needed a new energy. Do we want to become carbon neutral by 2050, something that substitutes the baseload power from fossil fuels? And if we want to do that, whatever that energy is, we will need to install about 300 gigawatts of power. And if we want to do that with fusion, that means that we will have to build 300 demo reactors at gigawatt electric level each in the US alone, and only for electricity generation. So this becomes a really, really hard problem. So how do we see at MIT that we can improve this roadmap? So we look at our plot here that we had of the fusion gain versus size and magnetic field, and we thought, okay, it would be fantastic if we can build machines that operate in this region at high magnetic fields, that leads to a small size and therefore a cheaper and faster way to build machines. However, we had this limit of low temperature superconducting magnets, so we had to come up with something else. And actually, we looked into our colleagues in materials science, and we found out that they developed a new generation, quite recently, a new generation of high temperature superconductor technology that allows operation at high magnetic fields. So yes, this is very qualitative, but you can get the idea here. We have the magnetic field, temperature of operation of the superconductor, and the current density that it can carry. The previous technology with low temperature superconductors have a quite limited operation at low magnetic field, very low temperatures, near zero, absolute zero, and very small current density. With the new technology of high temperature superconductors, that window actually opens quite a lot. So it opens the possibility of operation at high magnetic fields. And that's going to be a game changer for fusion energy. And now we're learning how to build cables out of those superconductors. And with those cables, we're going to build coils. And that will truly enable the design of fusion devices that work with unprecedented magnetic fields. And we are working at the PSFC on that concept. And actually, this comes from both MIT and the private company Commonwealth Fusion Systems, which is an MIT spin-off. We are working together to realize the high field path to bring fusion energy to the world in a timely and cost-conscious manner. So the way we see this roadmap that I showed you earlier is actually very similar to the steps that the fusion community has established before. First, we want to demonstrate net energy. We're going to do that in a device that we call SPARC. is right now under design, and we're going to demonstrate the magnet technology by June this year, very soon. We're going to have a first plasma by 2025, and we're going to reach the break-even milestone, or even Q greater than 2, soon after. And after SPARC, we're going to build a demonstration, a pilot plant, fusion power plant, that we call ARC. And something important to realize here is that this is all at scale, which means that SPARC will be of the size of our medium-sized devices, and ARC will be of the size of big machines, but that we have already built, not as expensive, not as complex as, for example, ITER. So let's talk a little bit about SPARC. So SPARC is a net energy, compact, high field, DT fusing device. The concept was presented to the fusion community at the annual APS-DPP meeting in Portland, Oregon in 2018. We have worked very hard and we have improved it. And the latest version, what we call the V2, has been thoroughly studied and peer-reviewed, and we have published in last September a special issue in the Journal of Plasma Physics with all the information about the physics basis of this machine, with 7 papers, collaboration between 12 institutions, 47 authors. All that was just some months ago. And we have been on the news, the New York Times, MIT News, and we even got Stephen Colbert to talk about fusion in his late night show. So that was quite fun. So, okay, but all this looks like a press release. So let's go back to physics. What is SPARC? So when we define a new tokamak, we typically give 2 things. We give the cross-section, how it looks, the cross-section, how it looks, and a table of parameters of that tokamak. But since I don't expect you all to know what all those parameters mean, let's go one by one what those numbers really mean. So the major radius of the torus is 1.85. That's a medium-sized device, which means that it's cheaper, faster to build. Remember that the biggest tokamak we have ever operated is JET, has a major radius of 3 meters. So this is smaller than JET. The minor radius, this minor radius means that the aspect ratio, A over R, is standard. So we expect no surprises in terms of plasma physics. We have operated tokamaks in that regime for many years. This magnetic field, this 12 Tesla, is the magnetic field that will be in the center of the plasma, and that's unprecedented at this size. And this is where all the magic happens. This plasma current means that the normalized current, Q star, the safety factor I told you earlier, is the same as ITER. So we're not taking extra risk. ITER was designed many years ago. We have thoroughly studied those plasmas. We understand how to make them work. We're not taking extra risk in that sense. This is the normalized density, and we're actually taking less risk than ITER in terms of the normalized density. We don't want that factor to be above 1, because then you enter in problematic regimes. So we are well below that. This input power, 11 megawatts, that's the external power that we're giving to the plasma, and that's reasonable. We have built machines that operate with higher power, and we know how. We know how to build those heating systems. And these are geometric parameters, elongation of the plasma and triangularity. Those are standard. We have built and operated machines with that already. We expect no surprises. So the takeaway from this slide is that we have built SPARC as robust as possible with a very robust foundation, because we want to make sure that it works and it will reach its goals. So, and then we can compare the cross-section of SPARC with other devices. This K-star in Korea, East in China is very similar, and then JET in Europe, which is bigger than SPARC. So there's nothing new here. We have built this type of machines before. So a mission of SPARC is break-even, Q greater than 1. That's the kind of the goal. And we chose a mission for SPARC of Q greater than 2 because we want to have some safeguard. We want to make sure that we have room to the milestone. So if we're investing so much time and effort on this, how do we make sure that SPARC will reach that mission? How do we really predict fusion performance? Because before I gave you some rules to know about the scalings of the parameters, but how do we really do that how do we model and predict that? So we have to take into account power balance. And with power balance, I mean something as simple as this. We have the evolution of the energy of the plasma is equal to the power input minus power output. Power input is auxiliary, like externally generated, like waves, for example. And the self-heating from fusion reactions. And as power loss, the losses, we have radiative power and we have transported power or conducted power, as you wish, some heat flux. And let's see how plasmas behave when we heat them up. So this is the cross-section of SPARC. We take, for example, this middle, we look into the center of the plasma. So we take a look at the middle line here, and we can plot things like the temperature. And when we start heating the plasma up with waves, the temperature goes up. There's some phenomena that happen, but don't worry too much about it. And it will eventually reach some stationary state of the temperature. That stationary state is a state in which the evolution of the energy of the plasma does not change. And really the temperature that it reaches, and therefore the fusion power that it generates, is going to be just a function of the balance between power input and power output. And for power output, this guy here, this heat flux, this transported flux, it's going to be that's going to be difficult to calculate because that depends on processes related to turbulence. So because the temperature in the plasma and the pressure in the plasma has a gradient, that makes some modes to be unstable, and that leads to some micro instability, some micro turbulence that leads to higher heat flux. So if we want to really know what's the fusion performance of a machine, we have to understand this heat flux. So how do we do that? How do we do that for a SPARC? So to assess performance of a SPARC, we have taken a 3 steps approach. First, we have what we call data-based empirical models. We take our power balance equation that we had before, we have it in a steady state, so no evolution of the plasma energy. We have power input minus power output. And we do an approximation here, which is that we look globally at the entire plasma. So we integrate all the losses and we write them in this form. We have the stored energy of the plasma over a parameter that we call the energy confinement time. And that energy confinement time is going to determine how fast you're losing your energy in the plasma. And that energy confinement time is a parameter that we have measured for many years in many devices. We have measured it and we actually have fitted models to that. We have what we call power loss. So with tokamak parameters, we have taken the plasma parameters of many tokamaks and we have constructed this regression to the energy confinement time. And if we plug in SPARC parameters, it turns out that we are in the range where we have already measured. So we have already measured energy confinement times of the level of SPARC. And we take that energy confinement time and we do a couple of more calculations and we end up with what we call the operational contour of a plasma. I'm not going to go into detail because I don't have much time, but just to show you that what I'm plotting here is where the tokamak can operate in terms of what density and what temperature. And this yellow region here of the parameter space indicates the region that SPARC will produce a Q, a fusion gain greater than 2, and will operate safely. And what is more important is that for SPARC parameters, we have identified an operational point that not only produces Q of 2, but it produces a Q of 11. So it produces 11 times as much energy as we put in. So this is fantastic. And to check that, instead of just basing our calculations on empirical models, we have done what we call integrated simulations, physics-based integrated simulations, which are similar in the sense that we take the power balance equation, we rewrite it in a way that takes into account the tokamak geometry. And the heat flux, this guy that I told you earlier that it was hard to compute, hard to calculate, in these simulations, what we do is to approximate it based on what modes, what instabilities exist in the plasma. Again, I'm not going to go into detail. This is something that has been done for many years. And taking that approximation, we can predict things like what the density of the plasma will be, what the temperature will be, and therefore we can predict how much fusion the plasma will generate. And if we take the same parameters as we used previously in the empirical simulation, the empirical model, we predict that SPARC could produce Q of 9. So it's not Q of 11, but still we're very close to that value. It's definitely above the Q equal to mission. And to even be more sure about that, we actually checked that approximation to the turbulence, to the heat flux that I mentioned in the previous slide. We checked it with the state-of-the-art physics simulations. So there is something called the Gyrokinetic equation that is able to describe turbulence. We ran that in supercomputers, for example, at the NERSC supercomputer in California. These simulations take in the order of 100,000 to 1 million CPU hours per simulation, so they are very, very expensive. But we can predict the turbulence structures, and we can estimate the temperature that is reached in the core of the plasma, and compare it with our previous simulation to make sure that at least we are in the same range and in the same regime. So we check with this the assumption that we made earlier. So the takeaway of this is that all approaches, empirical, physics-based integrated models, and the state-of-the-art physics suggest that SPARC will achieve a Q between 9 and 11, and that's much higher than the mission of Q of 2. That's a lot of margin. That gives us a lot of confidence that the device will succeed, and that opens the possibility for the extensive study of burning plasmas. So that's very exciting, but we still have to think of what's the final goal. So SPARC is going to be a test bed for ARC, which is going to be our pilot plant, because we eventually want to put electricity into the grid. We want to have a reactor that produces heat, that brings steam to a turbine and produces electricity. However, from current experiments to power plant relevant plasmas, there is a jump in plasma physics variables or parameters or other engineering parameters of interest. So all our experiments nowadays are a little bit low in some of those. It's true that both our empirical and physics-based models do provide confidence that ARC's design point is feasible, but still we have large uncertainties in how a fusion power plant will behave. And the goal of SPARC is actually to reduce those uncertainties, to bridge current experiments with the operational point of a reactor or of a power plant like ARC. So SPARC will inform trade-offs as we complete the ARC engineering design, which is basically our final goal. So that's all that I had today. So thank you very much for your attention. I would like to point out that this talk was inspired from past presentations given here at IAP and PSFC seminars. And also I leave here also the papers that we published last September, the open issue, special issue in the Journal of Plasma Physics describing in detail all the SPARC physics. And now I purposely left about 10 minutes for questions, but we run out of time. Also, you feel free to email me and we can talk. And also we can discuss how to get you involved if you're interested in this project. So thank you very much.